Welcome back, everyone, to another deep dive. And today we're going to be looking at something pretty mind-bending,
Yeah,
automated theorem proving.
really cool stuff.
So imagine trying to prove like a really complex mathematical theorem, but there are like infinite possible solutions.
Right.
How would you even begin to tackle that?
Well, it's a fascinating challenge, and uh, at the heart of it lies this concept called instantiation.
Okay.
And you can think of it as like
Yeah.
finding the right values to plug into these logical statements to make sure that they're true.
So like,
Finding the exact right pieces of a puzzle
yeah.
to make them all fit together.
Yeah, like a puzzle.
But here's the catch.
Yeah.
Sometimes those puzzles have infinite pieces.
Okay, that sounds like a lot of pieces.
It is.
Yeah.
And it sounds like a recipe for a computational meltdown.
Oh, yeah.
But I understand there's been some really interesting research on how to tackle this problem,
There has.
even using machine learning
Yeah.
to do this.
That's right.
Okay.
So we'll be exploring this groundbreaking 2025 paper.
Wow, 2025.
Yeah.
Okay.
From the Journal of Symbolic Computation. And it's authored by some of the leading minds in this field. And they've actually managed to train a neural network to make these educated guesses about these instantiations.
Hold on, a neural network.
Yeah.
So I always think of neural network as like image recognition or like
Yeah.
language processing.
Right.
But we're talking like hardcore mathematical logic here.
Yeah.
So what's the connection?
Right. So to understand that, we need to touch on this very fundamental concept called Herbrand's theorem,
Okay.
which basically tells us that for any provable theorem, a solution exists
Okay.
somewhere within this vast, potentially infinite set of mathematical terms.
Right.
The trick is finding it.
Okay. So it's like
Right.
knowing that there's like a specific grain of sand on a beach that holds the key to our theorem,
Yeah.
but we have no idea where to start digging.
It's a good analogy. Okay. And is this where traditional automated theorem provers often stumble?
They do.
Okay.
They employ all sorts of clever logic and search strategies,
Right.
but they can get really bogged down in this vast search space.
Especially when dealing with more abstract mathematical concepts.
For sure.
Yeah, so I've heard of some of these systems like iProver
Yes.
and what are called SMT solvers.
Yeah.
They're incredibly powerful,
Very powerful.
but it sounds like even they have their limits.
Exactly. So if these traditional provers struggle with these vast search spaces,
Yeah,
what's a better way?
right.
And that's where this really innovative neural network approach comes in.
Okay.
The researchers have designed this system that combines a graph neural network,
Okay.
or GNN for short,
Got it.
with a recurrent neural network, or RNN.
Two types of neural networks.
Two different types.
Wow, that sounds pretty sophisticated.
It is.
What do they each bring to the table?
So you can think of the GNN as the reader. It analyzes the structure of the problem, like a map maker, charting the terrain of our metaphorical beach.
Got it. So
It identifies these connections between the different concepts
yeah.
and figures out the overall layout of the problem.
So it's like setting the stage,
Yes.
getting a sense of like the big picture.
Exactly.
Okay, but how does it actually find that crucial grain of sand? Is
Yeah.
that where the RNN comes in?
That's where the RNN comes in.
Okay.
It acts as the pathfinder.
Okay.
So based on the map that's created by the GNN, the RNN proposes these candidate instantiations,
Okay.
essentially suggesting places to start digging for that grain of sand.
So it's not just randomly guessing.
Yeah.
It's making educated guesses
It's making educated guesses based on the structure.
based on the problem structure.
Yep.
Okay, and this is where the learning part comes in.
That's right.
Right.
So to train this system, the researchers used this vast collection of real-world math problems called the Mazar Mathematical Library.
The Mazor Mathematical Library.
The Mazar Mathematical Library.
Okay.
And they essentially gave the neural network a crash course in theorem proving.
Okay.
Yeah,
So they fed it tons of problems and said, figure it out.
basically.
But how do they know if the neural network's guesses are actually correct?
Right. So they started with random guesses,
Okay.
and they were checked against this separate program called a ground solver.
Okay, a ground solver.
A ground solver.
What is that?
You can think of it as the referee
Okay.
that determines whether a proposed solution actually works or not.
Got it.
And this is where it gets really fascinating.
Okay.
These successful solutions were fed back into the network.
Okay.
allowing it to learn and refine its guessing strategy over time.
So it's like playing a game of like logical hot or cold with the neural network.
Exactly.
Okay.
Constantly getting better at finding the right answers.
And this all comes from a 2025 paper.
A 2025 paper.
That's cutting edge stuff.
It is.
What were the results like?
The results were really impressive.
Okay.
Starting from scratch,
Yeah.
this system managed to solve almost 20%
Oh.
of the unseen test problems they threw at it.
Oh, the unseen problem.
Unseen problems.
Right.
Remember, these are problems it's never encountered before.
Wait, 20%?
20%.
That might not sound like much to our listeners,
Right.
but in a field as complex as automated theorem proving,
As complex as this.
that seems like a pretty big deal, right?
It's a significant achievement,
Okay.
especially considering that. Especially considering that it even managed to find solutions that stumped those traditional provers we talked about earlier.
Oh, wow.
Like iProver.
So it's not just mimicking existing methods.
Yeah.
It's actually coming up with like novel approaches.
Brand new approaches.
That's really intriguing.
Yeah.
I'm curious to know more about the implications of this 20% success rate.
Yeah. So, see, this isn't just about solving math problems.
Right.
This 20% success rate hints at a future where machines could independently verify complex software,
Oh, wow.
discover new scientific theorems,
Okay.
or even design entirely new mathematical concepts.
Okay, now we're talking about some serious potential.
Yeah.
But hold on. How do we know that these solutions are actually valid
Right.
and not just like clever tricks?
Of course.
Could you walk me through that?
It's important to remember that this neural network isn't operating in a vacuum.
Right.
The solutions it proposes are still checked for validity using those ground solvers.
Oh,
Think of them as the ultimate fact checkers.
right.
Making sure that the logic holds up.
So there's like a human element still in the loop,
There is.
making sure that the neural network isn't just like pulling a fast one on us.
Exactly. It's a collaborative process.
Okay.
The neural network proposes solutions, and the ground solver acts as the final judge.
Got it. So it's not about replacing human mathematicians.
No,
It's more about giving them a powerful new tool.
that's a great way to put it.
Okay.
And this tool has the potential to revolutionize fields beyond just mathematics.
Like what?
Well, think about software verification. Right now,
Yeah.
ensuring that complex software is free of bugs and vulnerabilities is incredibly time-consuming and expensive.
It is.
But imagine a system that could automatically identify potential issues,
Okay. Yeah.
saving countless hours of work
Right.
and making our technology much safer.
That would be a game changer,
With-
especially as our software systems become increasingly complex.
Absolutely. And it doesn't stop there.
Okay. Where else?
This technology could also have a huge impact on AI development.
Okay.
Imagine AI systems that can not only process information, but also understand and reason about it on a much deeper level.
Yeah.
That's the kind of breakthrough this research is pointing towards.
Okay. I'm starting to see the bigger picture here. This
Yeah.
isn't just like some esoteric mathematical exercise.
No,
It has real-world implications that could affect all of us.
absolutely. And this is just the beginning.
Right.
We're only scratching the surface of what's possible when we combine the power of machine learning with the rigor of symbolic logic.
So for our listeners who might not be familiar with like the term symbolic logic,
Right.
could you just break that down for us?
Yeah.
What does that actually mean?
So symbolic logic is essentially a way of representing and manipulating information using symbols and formal rules.
Okay.
It's the foundation of mathematics, computer science, and even the way we structure arguments in everyday language.
So it's like the underlying language of logic and reasoning.
Precisely.
Okay.
And what's groundbreaking about this research is that it shows that a machine learning system can not only understand these symbolic structures,
Yeah.
but also contribute to manipulating them in a meaningful way.
So we're like blurring the lines between the rigid logic of computers and the more flexible, intuitive thinking that we associate with humans.
We are.
That's pretty mind-blowing.
It is, and it raises some fascinating questions about the nature of intelligence itself.
Right.
If a machine can learn to reason symbolically, what does that tell us about our own cognitive abilities?
That's a deep dive for another day.
Exactly.
But for now, I think we've covered a lot of ground.
We have.
From the challenges of instantiation to the surprising role of neural networks in theorem proving.
For sure.
We've seen how this research has the potential to impact fields ranging from software development to AI.
Right.
And we've even touched on some of the philosophical questions it raises.
Yeah.
And just to bring it back to our listeners, why should they care about all this?
Yeah.
What's the takeaway message here?
At its core, this research is about pushing the boundaries of what computers can do.
Okay.
It's about creating systems that can not only crunch numbers, but also grapple with abstract concepts and solve problems that have stumped human minds for centuries.
So it's about like augmenting our own abilities and expanding our understanding of the world around us.
Exactly.
Okay.
And who knows, this type of system might one day help us tackle challenges we haven't even imagined yet.
Now, that's a thought-provoking note to end on. But before we wrap up, I want to quickly recap the key takeaways from our deep dive into automated theorem proving and the surprising role of machine learning.
Okay.
We started by exploring the concept of instantiation.
Finding those perfect puzzle pieces to make those complex logical statements click into place.
Finding those perfect puzzle pieces to make those complex logical statements click into place.
Right.
We talked about how Herbrand's theorem provides a sort of roadmap for this process,
Yeah.
assuring us that a solution exists somewhere within that vast sea of mathematical possibilities.
See it somewhere.
But finding that solution, well, that's where things get tricky.
That's the hard part.
Traditional automated theorem provers often struggle with this challenge,
Right.
especially when faced with abstract concepts and an overwhelming number of potential solutions.
Too many possibilities.
And that's where this revolutionary neural network approach comes in.
A whole new way of thinking about it.
Combining the power of graph neural networks and recurrent neural networks to tackle this problem in a whole new way. The graph neural network acts as the reader.
Yeah. Mapping the terrain of the problem.
Mapping the terrain of the problem and identifying connections between different concepts.
Right.
While the recurrent neural network acts as the pathfinder.
That's right.
Suggesting potential solutions based on that map.
Based on the map.
And through rigorous training on a massive data set of real-world math problems.
Huge amount of data.
This system has shown remarkable ability to solve complex theorems,
Yeah.
even outperforming some of the best traditional provers in certain cases.
That's really impressive.
This research represents a huge leap forward in the field of automated reasoning,
A big step forward.
blending the strengths of machine learning with the precision of symbolic logic.
The best of both worlds.
And it opens up a world of possibilities, not just in mathematics,
Right.
but also in fields like software development, artificial intelligence, and scientific discovery.
The possibilities are endless.
So as we wrap up our deep dive today,
Okay.
I want to leave you with a final question to ponder. Could this type of system one day help us unlock solutions to problems we haven't even begun to imagine?
That's a great question to think about.
It's a question that really highlights the potential of this research.
Yeah.
And it underscores the incredible power of combining human ingenuity with the power of these advanced computational tools.
It's a powerful combination.
We encourage you to explore this fascinating field and to consider the implications of this research for the future of problem solving.
Absolutely.
So until next time, keep those minds engaged and keep diving deep into the world of knowledge.
See you next time.